Section 8.2, testing the difference between two means. Independent samples, standard deviation of population 1 and standard deviation of population 2 are unknown. As with before, if we don't know the population deviations, we can use the t-distribution table. Very similar to what we were doing in the previous section, to see if there is a statistically significant difference between two populations, as the samples must be randomly selected, at least 30 or more, or a normal distribution, and the samples must be independent of each other. Now, as you can see here, the t-score is very similar to the z-score. The only difference is we have the s, which is the sample deviation. This is the difference between the two means in the sample. This becomes 0, the mu1 minus mu2. But it's going to go within the differences of the variances. If the variances are both equal, and they'll tell you if they are or not, what you take is you have to do a two-part formula here. As I said before, it's not hard, but it is very step-by-step. Number of samples minus 1 times the deviation squared of the first sample set plus number of samples minus 1 for the second sample times deviation of the second sample squared divided by number of samples 1, that should be plus number of samples 2 minus 2. And we'll go with examples of both of these. And then once we have this right here, this deviation hat, we multiply that answer times the square root of 1 over the number of samples of the first sample plus 1 over the number of samples of the second sample. We use our t-table, and our degrees of freedom are the number of samples for the first one, number of samples for the second one, minus 2 rather than minus 1 because we have two different sets. Now, if the variances are both unequal in the sample, we simply have this formula here. This is the sample deviation of the first set squared divided by number of samples, sample deviation of the second set squared divided by number of samples. We add those together, square root of all that. And then our degrees of freedom in that regard are found by the number of smaller samples. One set is 20, one set is 30. We take the smaller set, 20 minus 1, be 19 degrees of freedom. Very similar to finding population deviations with the z-table, where we know the population deviations. We have to verify that population deviation 1 and 2 are unknown. This is for using the t-table. Both samples are independent and random, and either population normally distributed or greater than or equal to 30. We set an alternate null hypothesis. They'll give us the alpha, and we have to find out what our make or break regions are. On A and B and number 4 here, we just went over this for the different variances for our denominator ultimately. And we're going to put it through there within our t-score and then determine if we fail the null hypothesis or we fail to reject the null hypothesis. Let's go through some samples here. The result of a state's mathematics test for random samples of students taught by two different teachers in the same school are shown. Can you conclude that there's a difference in the mean mathematics test scores of students of the two teachers? Use alpha equals 0.10. Assume the population normally distributed and population variances are not equal. So the variances are not equal. So before we go any farther, we're simply going to use population variances are not equal. So in a few minutes, we'll be using this formula. Now let's see here. They want to know if they're the same or different. So since they are different, that's two-tailed. And that will be two-tailed hypothesis. Mu1 is not equal to mu2. Null hypothesis then is mu1 equals u2. And like I said, since it's equal and not equal, it is two-tailed. Alpha 0.10. Now, we've got different variances, so we find the smaller of the two samples here. Sample 1 is 8. Sample 2 is 18. So 8 minus 1 is 7. So 7 degrees of freedom. So there's our 7 degrees of freedom right there. It's two-tailed, and then I want to know 0.10. Here's my two-tailed column row right here. 0.10 it'd be 1.895. So it'd be plus or minus 1.895, which is what I've written here. Now let's find, since our variances are unequal, let's find out our sample deviation combined. So sample deviation of 1 is 39.7, so it's 39.7 squared. Divided by number of samples, 8 here. The second one's 24.9 squared, divided by 18. And when I calculate that, I get 197 plus 34.45. That added up, ends up being, the square root of that is 15.21. That becomes my denominator here. So in my numerator, the u1 minus u2, my mu1 minus mu2 is 0. So that cancels out, and I got the 0 right there. Difference of 473 and 459. 473 minus 459 is 14. 14 divided by 15.21 is 0.920. So I got negative and positive 1.895. So anything less than that, I'd fail to reject. Anything greater than that, I would fail to reject. So that's my make or break, a negative 1.895 and plus 1.895. My t-score is 0.920. Said it is in the fail to reject region. It is an acceptance area, and that means the scores of the two teachers are not significantly different. And the earnings of 25 people with high school diploma and 16 people with associate's degree are shown below. Can you conclude that there's a difference in the mean annual earnings based on education? Use alpha equals 0.05. So the population normally distributed, the population variances are not equal. So as before, population variances are not equal. So I'll be using this formula right here when we get to it. Want to know if they are the same or not. So the null hypothesis would be equal. And then alternate hypothesis would be not equal. So it's two-tailed. It is equal, not equal. And since the variances are not equal, we use our two populations. High school diploma is 25, associate's degree is 16. 16 minus 1 is a smaller sample, which means 15 degrees of freedom. And 15 degrees of freedom, and it's two-tailed at alpha 0.05, two-tailed at alpha 0.05 right here. And that ends up giving us, let's see here, 2.131. So it's negative and positive 2.131. Anything less than negative 2.131 would be rejected on this side, and anything greater than 2.131 would also be rejected. And again, I found that out because it is 0.05, and it's 0.025 on each side, but the table allows us to find it quickly. So our first sample deviation is 5475. I square that, divide by 25, I get 1,199,025. My second deviation is 8,580. When I square that and divide by 16, I get 4,601,025. I add both those up, find the square root of it, 2408.33. And there is my combined deviation. My mu's equals 0, if we make that assumption. So I find the difference between 36,875 and 44,900 is negative 8.025. Negative 8.025 divided by 2408.33 is negative 3.33. And negative 3.33 is way out here. It is below the lower end of less than negative 2.131. So we would reject the null hypothesis and say that there is a difference between the average wages of a person with high school diploma versus associate's degree according to this data. A manufacturer claims its mean driving cost per mile of its sedans is less than the leading competitor. You conduct a study using 30 randomly selected sedans from the manufacturer and 32 from the leading competitor. Results are shown below. Alpha 0.05 can support the manufacturer's claim. Assume the population variances are equal. So the population variances are equal, which means it's the two-step formula we have to find here. And first we have to find our hat of sigma, which is right here. We'll do that in a moment. So our null hypothesis would be is greater than or equal to, because they're making the claim on the alternate that manufacturing mean driving cost is less than leading competitor. So it's less than, it's pointing to the left, so it's one-tailed, as left-tailed. Alpha 0.05 for one tail. We would actually combine the two sample sizes, 30 and 32, and then subtract 2. So 30 plus 32 is 62, minus 2 is 60. And that would be 60 here, way down here, 60 degrees of freedom, and it is one tail at 0.05. We go to the first row here, 0.05, one tail, and that would give us 1.671. So it'd be negative 1.671 since it's left-tailed. And then we got there. So first we're going to find our our sigma hat, which is n minus 1, number of samples the first one, minus 1, times the sample deviation squared, plus second number of samples minus 1 times second number of samples deviation squared, over n1 plus n2 minus 2. So this is a little messy here, not hard, but let's do this. 30, the first sample is 30, minus 1 is 29 times 0.05 squared. And that gives us 0.0725 right here. Second one is 32 minus 1, which is 31 times 0.07 squared. That gives us 0.1519. 0.0725 plus 0.1519 divided by 60, which is our number of samples combined minus 2, gives, and the square root of all that is 0.061. Now we take the 0.061, and that is our sigma hat, times the square root of 1 over 30 plus 1 over 32, which is equal to 0.254. 0.061 times 0.254 is 0.0155. That is our denominator, and our sigma, or deviations for the populations combined. My differences are 48 cents per mile on the first one, 51 cents per mile on the competitor. 40 minus 51 is 0.03, negative 0.03, divided by 0.0155, which is negative 1.94 for the t. When we found a negative 1.671, that's our make or break, and our t is less than that, negative 1.54. So I reject the null hypothesis. It's less than in the acceptable region, but it actually supports that they do have less driving costs per mile. A manufacturer claims that mean driving costs with minivans is less than its leading competitor. You randomly select 34 randomly selected stamps from manufacturing, 38 from leading competitor. Results are shown below. At alpha 0.10 can support the manufacturer's claim. Assume the population variances are equal. So just like before, we are going to assume population variances are equal, which means we have to do the two-step formula to find our combined deviations. Let's see. So the claim mean cost of minivans is less than. So that is the alternates less than. That's the claim, which means the null hypothesis has to be the equality statement. Mu1 is greater than or equal to mu2. Let's left-tailed because it has the less than point at the left here. And it wants to know 0.10. So let's see what it is here. And because it's equal variances, I'm going to add 34 plus 38, which is 72, minus 2, which equals 70. Now, what we have here is I have one at 60, and I have one at 80. So we're going to make a guesstimate. It's going to be right between those two, and it's at 0.10, one-tailed. So 0.10, one-tailed is right here. And let's see what we get. We get at 60, it's 1.296, at 80 is 1.292. So we're going to find right between those is 1.294. And that's how I get this. Since I'm on the left side, so it's negative 1.294. So that's our critical make or break region right here. Anything to the right of that, we'd fail to reject, basically accept it. And left of that, left of this arrow, we would reject it. So let's find our sigma hat first. Number of samples minus 1 for the first one, which is 34, minus 1 is 33, times sample deviation squared. And let's see, the sample deviation, the first one's 8 cents, 0.08 squared. 33 times 0.08 squared is 0.2112. Second one's 38 samples, minus 1 is 37 times 0.07 squared is 0.1813. Number of samples, 38 plus 34, 72 minus 2 is 70. 0.2112 plus 0.1813 divided by 70, and the square root of all that is 0.075. So 0.075 goes right here, and that is, then we'll apply that times the square root of 1 over 34 plus 1 over 38, which is the size of the two samples. That ends up being 0.075, our number we found 4 times 0.236, which is 1 over 34 plus 1 over 38, add together, and the square root of that is 0.236. That's 0.0177. So our combined deviation is 0.077. Our mu's are equal to 0. And then 0.52 minus 0.54, the difference is negative 0.02. 0.02 divided by 0.0177 is negative 1.13. And negative 1.13 is close, but it is in the fail to reject region. So we would fail to reject the null hypothesis and shows there's not a difference between the cost of driving from Round between the two different minivans.